Okay. Yeah. Ready, yeah.
Okay, let's see. Not sure what order we should go in. First, the easiest problem, it seems by
Let's skip
far,
M. Let's skip M. Yeah.
is M, but it's pretty easy. So after that, what's next? It seems like maybe A,
D. I think it's D. Yeah.
D, I. So maybe start with D.
Okay.
Oh man, D is just annoying math.
Yeah. D is just.
Yep.
But yeah. But I guess I'm just curious to see how people coded it. I suspect there'll be different.
So the problem is, like, we have time 1 and we have time 2, and we want to know, also we have some like interesting angle that we care about called alpha, and we want to know how many times between T1 and T2 where the hour and the minute hand have exactly an angle of alpha. And alpha is either 0, 90, or 180. Okay. So the problem's a bit annoying because like there's different cases and stuff, and there's some simple parts that are easier to deal with, like we can figure out how to parse the input. We can also realize that the angle of 90, there's 2 ways to make the angle of 90. Like it can be either way and both count as 90. So we can simplify that by saying like we count 90 and 270. Right? Like if we think the angle is only to the right or something, then we can easily deal with that. So the question is really like, how do you find the interesting moments where they make the correct angle? So how do I make this bigger? So my approach was to realize that there's like, let's say that these are all the possible times. If we can compute all of the moments of time where we get an interesting angle, either like 0, 90, 180, or 270, like if we can find all of those points pre-computing, then when we have one of these queries between 2 moments of time, like there's actually very few of them, so I could just like directly count how many, like just iterate and check if they're between the 2 times. Yeah.
So how do you what do you enumerate to find out the interesting time? Do you? I guess it's basically the balance between how much math you do and how much programming you do. So.
Yeah. So I tried to avoid math by like iterating all possible times.
Okay.
You can see from the sample explanation that they could be, the interesting time could be like a fraction of a minute. So let's work out like what's actually going on. So let's say that a time is like how many minutes. So it'll be like 60 times how many hours have passed since 0, 0 plus number of minutes. So now the time is just one number. We can also compute like what's the speed that the hour hand moves? What's the speed that the minute hand moves? So you can compute those, and eventually you'll kind of see that the discrete interesting moments of time will have to be like a multiple of 1/11 of a minute.
Okay. So basically you enumerate through all those time instants and check their angle?
Yeah, so I say instead of the moment of time being defined by 60h plus m, I actually define it by multiplying this by 11. And then I check all possible integers between the time 0 and the time given by like 2359. Or maybe it was 2400. But so basically there's like a finite number of interesting moments of time. And then for each one I calculate what position is the hour hand in, what position is the minute hand in, like does the angle create 0, 90, 180. So then when I have a query, I just like check all of the interesting times that I found, and there's not very many of them, so it's fast enough.
So just curious, did anyone do without enumerating through all this 1/11th of a minute?
I mean, I just like calculated it for each one. Like for each case, like 0, 180.
Okay. You did math for each. You calculated which times it works.
Yeah, basically, it's just bash.
Yeah. That works too. Yeah.
So it's just, do you prefer math or programming to be your pain?
Good. Yeah. I did similar to Riley, but I sort of did for each query I enumerate through the interesting time, but I think it took me 2-3 submissions because of corner cases. Okay.
I think I didn't have a wrong submission. No, I did. I forget what it was.
Cool.
Yeah, I'm not sure. So what's next? Maybe A?
I, is that either A or I, it doesn't matter which one.
Yeah, I think I was easier, at least for me.
Let's go over I guess. So let's see. So this is an interactive problem, which is kind of unusual if you've seen it for the first time. But so if you haven't seen an interactive problem, the idea is that it's not as simple as like the computer just gives you all the input and then you get all the output. Instead, like the task at hand, like you do something and the program can respond. So it might be like you ask for some information and it gives you an answer in this case. Or it could be like you're playing a game and you want to win the game. So you have to like find the correct strategy. So in this question, there's like hidden information and you have to find, your task is to find that information by asking like specific kinds of questions. You can ask, so the information that's not known to you is that there's some sort of matching between switches and lamps. Each switch corresponds to some lamp and you don't know which one. And what you can ask is, you can choose a subset of the switches and it'll tell you which lamps were lit, but it won't tell them in the same order. It'll tell them in like an arbitrary order. So like if I ask switches 2 and 3, it will respond with switches 1 and 3, or it might say 3, 1. Either that or it sorts them, I forget. But either way, we can't tell whether this should be 2 and 3. We can't tell if 2 controls 3 or 2 controls 1, just from this one question. But the idea is that if we can ask at most 32 questions, can we find the exact correspondence between switches and lamps? Does that make sense?
Mm-hmm.
So let's think some like so definitely we could do it in n queries, which is pretty obvious. You can just like try one switch at a time, but that's too many queries. Another thing you can so in order to improve this, we realize that we have to ask some queries where there's multiple switches in the same query, and we need to sort of separate them out. Like we can't have, it's like for any 2 switches, they must not appear in the same set of queries, right? like, so say we have two switches like 1 and 2, and then each quarry either, so suppose each quarry either had both switches 1 and 2, or it had neither switches, then we clearly can't tell which one matches to what lamp. So this gives us an idea of how many subsets of quarries are there, right? So there's 2 to the 32 different subsets of quarries. So like say we have quarries 1 through 32. Maybe for the first switch, we ask it in the first query. The second switch, we ask it in the second query. Then the third switch, we ask it in both, right? And so we can use the binary representation to figure out which queries we can ask it in. And then from this point, you should try to figure out, given the lamps, how do I reverse it and uniquely identify for the switch which lamp it's in, or which lamp it corresponds to. Does this make sense?
Mm-hmm.
Any questions or anything to add?
Yeah, since I actually still don't know why my code is wrong, but that will I'll probably need you guys' help, but it'll be afterwards. So I'm pretty sure I have the basically correct logic, but yeah, yeah.
But yeah, that's the solution. And interactives, even if the solution is a bit simple to state, it can be like a little more challenging to code because there's some issues with like flushing the output and things like that. So even if it's simple, it can be a bit tricky to code right. Next problem is A, which was personally my favorite problem. So the problem is there's a grid, and we want to know how many ways there are to color it so that like a certain sets of rules are satisfied. So the rules are that there's 3 colors, red, green, and blue, and each every edge has to be painted one of those 3 colors. And for each unit square, so this is the interesting one. So each square has to be touching exactly 2 colors. So for example, this one's red and green, this one's red and blue, this one's red and blue, this one's blue and green. And the rule is that of those 2 colors, each one has to appear exactly twice. So like it can't be red, green, 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 and it can't be like, so yeah, it can't be like all one color, it can't be all 3 colors appearing. Yeah, that's the rule. So 2 colors appear and each one appears twice for each square. And so yeah, the question is to count how many ways mod a large prime, because the answer could be too big to store in like a usual integer. So the constraint for the number of rows is pretty small, which usually means it's something like bitmask dp, meaning like for example, a similar problem is a problem where that appears would be like how many ways to tile like how many tilings of an n by m grid with dominoes. So if you've seen problems like this, and then this would be where like n is small. So if you've seen problems like this, then the small constraint kind of triggers some thoughts about a bitmask dp. But the really interesting thing is that it's hard to make that work out, and I don't think it can work out because like 3 colors is too, it makes it too hard to make that work out. But instead, there's actually like a mathematical formula for the answer. And here's how you can arrive at it. So like say we have a square, the idea is if we know the colors of these two edges, we can think how many ways there are to color the bottom, like the bottom edge and the top or in the right edge. So if the top and left edge have the same color, then these have to be the same color. But there's two different choices for what color you can make them both. So like if these were red, red, then these could be green, green, or blue, blue. So there's two choices. And then let's think about the other case where the top and the left edge are different colors. Then the options are either, so we already know that the two colors are say A and B, and each color has to appear twice. So these also have to be A and B, but it could be either order. So again, there's two choices. So now the idea is we have this grid. What information would be enough so that like each of those two choices would be enough to like fill out the rest? Sort of like what's the smallest amount of information in the coloring that would like uniquely identify the entire coloring, because you can apply like the two choice rules like to fill in the rest like as independent choices. So you can think like if the topmost row in the leftmost column, like if we know all of these colors, then we apply the rule to here. There's two choices to fill in these. Then we apply here. There's two ways to fill in these. There's two ways to fill in these, and so on. And this cell, there's two ways to fill these in, and so on. So like if we fix the initial information in the top row in the leftmost column, then there's 2 to the nm ways to fill it in.
So this set of problem, I guess a lot of the parameters are intentionally misleading. Yeah, even the I one, the 32 is a little bit misleading, I would say. Yeah.
Much too large, yeah.
Yeah.
Yes.
But yeah, this one is definitely misleading. So I thought, yeah, it's a bitmap DP. At first, I thought if I use the 3 color, it'll be too much. But then I realized all I really care about is whether this one is the same or different from the above. I thought I had the right insight, but then it's can't work out how the recursion works. So
yeah. So I was also stuck in thinking that it must be bitmaps DP. But then I realized that didn't make sense in terms of how many people were solving it.
Right, yeah. 2 hours into this, I had something else, so I didn't do the rest. Yeah, but I was also surprising why so many people were solving it when it's
I think, and my way of arriving at it isn't maybe the only one. Maybe you could like so some other ways would be like, you could brute force, you could write a brute force, find the answers for small sizes, and then try to notice a pattern. And because the formula is pretty simple, you could like look at the factorization and then find the pattern and then code it. Another way is someone was saying like, if you imagine randomly assigning colors, you could think, what's the probability that a given cell has the property? And you could assume that those probabilities are independent.
I see. Nice.
So if you make some like unjustified assumptions or don't understand the solution, you can still kind of arrive at it.
Very nice.
But yeah.
Which regional is this? Is this the Trung know which?
This is 2019.
It's Central Vietnam.
I mean, this is a part of Vietnam. Okay.
Yeah.
I want to know where the problem setters are so devious. Intentional design parameters.
I am very familiar about these.
Let's see, what's next?
Geo is probably the next easiest. I solved that, so.
No, G is much harder than algebra.
No, G is very easy. I solved
No,
G,
G
but
is
not
hard.
A.
G is
No,
hard.
G is not hard.
G is
Not
hard.
I solved it, therefore it's not hard.
I think H is easier.
Really?
Yes.
H and L is much easier.
Oh my god.
Yeah,
L wasn't easier than G.
well, it
Maybe.
doesn't matter. Yeah. We don't have to do it in exactly. We don't have to have
G has like a ton of cases.
There's like only like a few.
I think
maybe
H is
three or
simpler. Maybe
Yeah.
let's talk about H.
Sure.
So in the problem H, like maybe you've seen these puzzles before,
Yeah,
Where?
it's-
where so the rule is like you have to fill in the grid with black and white cells, and then each row and column tells you like the pattern of black cells, like the sizes of the segments. So in here there's 1, 1, 1, 1, or in here there's 1, 1, this segment's 2, and 1. So it tells you the lengths of the segments and what order they appear in. So this problem is they tell you the patterns on the rows and the columns, and you have to count the number of solutions that satisfy the rule. Make sense?
I noticed the constraints were really small for this problem, so it seemed like very brute forcey, but I couldn't figure out a way to set it up.
Yeah, so the constraints are very small, so it immediately tells that you should like brute force. But because it's 6 by 6, let's think how many possible solutions are there if you ignore like how many ways there to just to fill in the grid? There's 36 cells, and each one can be white or black. So there's 2 to the 36 ways, which is, how big is this? It's definitely bigger than, say, like a billion.
It's like 10 to the like 10 or 11, right?
10 to the 9 times
to the 6 billion.
times 64 or so.
Yeah.
It's about that. Now, the general rule of thumb is that 10 to the 8 is about a second. So this would be way too big to brute force every single solution and then check if it's if it meets the row and column constraint. So what else can we do? We can maybe think for a given row, how many ways are there to satisfy like the row constraint? We might guess that there's not that many. Like if we know the segment lengths, then there can't be that many bit masks that satisfy a given row constraint. And the worst case I found was the constraint 1, 1. And there's 6 cells. You could have here. Or here. So that's 1, 2, 3, 4, 5, 6, 7, 8. Wait, did I miss one?
The ninth one is or
This one's invalid.
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I found a case where there's 10 for a given row. But I wasn't able to think of something with more, and like if there's lots of segments, then there's not very many positions they can be in. Like they're pretty restricted. And if there's fewer segments, then sort of there's not many like independent choices. There would just be like how many ways to put one segment, which would only be 6, at most 6.
Yeah, so my logic is each row there are 2 to the 6, 64 possibility, and this need to be divided into maybe like a dozen different configurations. So each one shouldn't be too large. Mm-hmm. Even I didn't count the max like you did. Yeah.
So I think so I believe it's something like there's 10 ways you can do each row at most 10. Could be less.
Oh, so you just iterate through every single like row possibility and then
you check the column, yeah.
Yeah, so it's like iterate over all ways the rows can be satisfied, and then check for each one if the columns can be satisfied. And the complexity will be, it'll be something like 10 to the 6 times. And then for each column, you have to check with each cell in there. And this is reasonable enough to pass.
Okay.
Yeah, so I added, I made the change to the problem set by using this one because at least traditionally, ECNA Regional has this, almost everyone had one of this game, this kind of searching and pruning, sometimes requiring pruning kind of problem.
Mm-hmm.
It's fairly brute force, it's a kind of a search problem.
Although if the constraints were larger, this would be a much harder problem though, right?
Yeah, then you need to do something clever, not so
Okay.
any of this kind of, I guess these kind of things are traditionally it's covered in like AI course. I don't know whether our current AI course, because you basically you search for solution while searching, you can also do pruning. So there are a lot of heuristics, and sometimes pruning is helpful. Sometimes actually when you're doing pruning, you are checking at every step. Sometimes it's actually make the overall performance worse. It depends on how much you can prune, which is oftentimes depends on the particular instance. So, but there are not that many of this kind of problem in CP, and the ECNA kind of search problem often are fairly more brute force kind of search type.
Yeah. So in competitive programming, sort of the standard is usually that you should have a complexity or an idea of how the solution performs in the worst case, because because like it could be any possible test case that you want your solution to satisfy. But for a lot of like standard things like sort of like brute force and pruning, then a lot of things like that is not obvious what the worst case is, or like the application is mainly for like real world instances, which might not satisfy the worst case.
Yeah.
So for example, in this problem, you don't need to do like backtracking and pruning. Instead, you can just like do a more clever brute force by ignoring like a large set of states that you don't need to check.
Yeah, so for example, one way of pruning is after you made the choice for the first two rows, you can already check whether that satisfies the column constraint. So if it doesn't, you don't need to check the rest of the row. But it's not needed for this problem. It just makes the code more complicated.
Mm-hmm. And let's see, what problem's next? G?
All right, let's go through L first, I guess.
Go through L.
I didn't read the problem description that thoroughly though, so it just seemed like annoying.
I actually misread it. I thought like we know exactly K cells, and we have to, and like the numbers can be anything in those K cells, and then we have to figure it out. But it's actually different. Instead, it's like we know all the positions of K of the values. So like there's one, so there's one value, which is 2, and we know all the positions of all the 2s. But anyway, the problem is like a Latin square is defined as like this grid where each row and each column has every number from 1 to n appear exactly once. And so the problem is that we know the positions of K of the values, and we want to either complete it as a Latin square. If there's multiple, we can print any. And if it's impossible, then we should print no. Seems good. So the constraint is that n is at most 100, and we have like 1 second. Okay, so we're moving on to L. So I think the key observation is that, say like we fix a value, like say we focus on the value 1. It'll appear in some number of rows and columns, and no row will contain 2 1s and no column will contain 2 1s. So let's say the rows are numbered 1, 2, 3, 4, 5. And the columns are numbered 1, 2, 3, 4, 5. Then actually the observation is that these positions, they are a matching between rows and columns. So like there's 5 rows and there's 5 columns. So if the cell 1, 2 is occupied, that means that these are matched. If 2, 1 is occupied, that means these are matched. This means 3 and 3, 4 and 5, and 5 and 4. So the set of positions for a fixed value is a perfect matching. So basically the question is, we want to, so like the question is, given the positions of the zeros, we would like to fill them with like we want to use those edges to make n minus k perfect matchings. Does that make sense?
Mm-hmm.
So it turns out that if we if we just wanted to say like let's just fill in one more value, right? Like we just want to know if we can fill in all the ones. Then we can actually do it arbitrarily. By just computing one maximal matching. So for example, in here, we might try here, here, and here. It's like we might find that this is a perfect matching and then fill them with 2s. Or we might find another perfect matching and then fill them with 3s. Did I mess up? I don't think so.
No, you're fine.
Right. So the amazing thing is that you can actually fill them arbitrarily. Like you can just compute one maximum matching at a time and then fill them in with those values. And then that removes some of the zeros that you can, so you can no longer use them for the next value that you fill in.
Is that guaranteed to work though? Like
Yes.
for all of them?
Yes. So let's think about why. So one thing that you can notice is that if we fill in like, say all the 2s, then we've just generated like another valid test case, right? So we just want to, like, we just need to prove like, given any valid input for this, that there's a way to fill in one more value. That's all we need to prove, right?
Okay.
So in order to do this, there's Hall's theorem. So let's look at what that says. It gives a condition for when a perfect matching exists. It says that a condition for a perfect matching is that given any subset of the items on the left, the number of reachable nodes on the right should be at least that many, right? Say it was less. Say that the set of nodes reachable from these two was only this one. Then we cannot make a perfect matching because the matched vertices of these of the things on the left have to be on the right, and they have to be distinct, and they have to be reachable from it. So sort of like by pigeonhole principle, if there was a matching, like one would have to be used more than once, but that violates the property of a matching. And it turns out that the condition is not only necessary, it's also sufficient. So the condition is like perfect matching exists. It exists if and only if, it exists. if and only if for all subsets of, I'll say like the left side, the set of reachable nodes, I'll just denote it by f of s, the set of reachable nodes from the ones in S, there's at least as many as there are in the set S. So this is the condition. So it's easy to see it's necessary, but it's hard to see it's sufficient, and I won't go over that. But does the statement of the theorem make sense?
Yes, we're good.
Okay. So now, like,
why the theorem apply here to show that?
So we would like to show that for any input that we could receive, there exists a perfect matching on the zeros. So we might, so here's how we can verify it. Given any subset of rows, let's look at only those rows. Yeah, let's say that, whoops, what's this? Okay, I don't know. Let's say that we ignore these. Like we're only focused on one subset of rows. So suppose that there's strictly fewer columns that are reachable. So like, let's say that there's only 2 columns that are reachable, that contain like a 0. That means all of this needs to be filled in. All of these values need to like contain non-zeros, right?
So what you need to be proved that if you are given a feasible instance, then no matter how you fill it using one perfect matching, you will still have a feasible instance, right?
Mm-hmm. So basically, I'm assuming for contradiction that there's some subset of rows that that violate Hall's condition. So now
after I've done one perfect matching.
Yeah, like assuming we're given an instance that satisfies like this input constraints. Okay. So I'm assuming for contradiction that there does not exist a way to fill in another value. So I'm assuming Hall's condition doesn't satisfy for some subset of rows. So like we're assuming that, and so I just showed here, that requires that all of these values must be filled in with non-zeros and they must satisfy the Latin square property. Right.
Yes, so.
Okay, let's see, why is this not possible?
I mean, because you'd need to like fill in too many basically, right? Kind of like a hand wavy way of thinking about it.
Let's see, I'm trying to think.
Yeah, I think it has to do with starting with a fully complete bipartite graph, so that it's.
Let's see. I'm trying like how do we prove that for some value 2 will appear in the same row or same column? So like, let's consider like a value 1, right? So how many occurrences, like how many rows can it touch, and how many of these columns can it touch, right? So the one, so among these cells, it has to touch the rows the same number of times as it touches the columns. Like it touches as many rows as columns, because otherwise a 1 would appear in the same row or same column. Like that can't happen. So every one among these cells touches an equal number of rows and columns, or same like for any other value. But what that means is that, but this contradicts the fact that we have strictly more like columns among these than we have rows. So this shows that there must be some, like the only way Hall's condition could not be met is if we had a violation of the input constraints.
Yeah, I see. Yeah. So essentially, from the initial empty, just you can, so long as you fill one number in a way that satisfies the condition, then you can always keep going to finish it.
Yes. Yeah. So as long as you can prove you can fill in one more value from any input, then that's enough to show that you can fill in all of the values, because you just end up with, because filling in one value just gives you another thing that satisfies the input constraints. So yeah, it's not, so it's, you don't have to like prove it with Hall's theorem to solve it, but like you can sort of guess that there's always a solution, and then it sort of makes sense that you can always fill in one more value, and you just end up with another input instance. But yeah, so wait, let's look at the complexity. We haven't looked at that. There's n values to fill in, and then each value we do max matching, and in the worst case it's like a complete bipartite graph, and the max matching constraint is like nm, where m is number of edges, and this is at most n squared. So overall the complexity is n to the 4th power. And actually you can see here that n is 100, so 100 to the 4th is 10 to the 8. And actually it'll be slightly less, I believe, but, or like you can do max matching faster than nm, but nm is good enough here. Is that good enough for L? Should we move on?
Yeah.
Maybe G now. Okay, so G says we're given some number and we can do these kinds of operations. We can either increase it by 1 or rearrange the digits. And we can't rearrange the digits to give it a leading 0. Okay. And the question is, we want to go from 1 to the given number in as few operations as possible. And we just have to find that number of operations, that optimal number of operations. Okay. So what I immediately realized is that we can think about reversing the problem, and I think it's more convenient to do. We can think, given a number, we want to bring it down to 1 by like the reverse of these operations, right? So the 2 operations we're allowed to do is decrease by 1. And reordering the digits in any way we like is actually just, it's the reverse of itself. So that operation doesn't actually change. We can just rearrange the digits however we like without creating leading zeros. So given these 2 operations, we want to take the given number x and bring it down to 1. So how can we do this? I found that maybe the best way to think about it is like, we want to, in order to bring it down to 1, we must first decrease the number of digits, right? Since we can't create leading zeros, rearranging the digits can never decrease the number of digits. So we always have to decrease the number of digits by the first type of operation, right? But in order to decrease the number of digits by 1, or to decrease the number by 1, to decrease the number of digits, it has to be from a power of 10, right? So everyone's with me?
Yeah.
So because of this, we can realize that we just need to solve the subproblem of, given a number, how do we bring it down to a power of 10, right?
Yeah, I just want to say I find this changing this from going up to going down, it's really nice, because so the other observation, so this you have to use +1 or subtract 1 to change number of digits. I also had that, but it still felt very messy how to go up. But I think turning it going down somehow make the process much more easier to think about.
Yeah, it's very common in, like, say, shortest path problems to think instead of going from start to finish, you're just going from finish to start by reverse. And in general, just like reversing processes is very common. It's a very common strategy to change the way you're thinking about a problem, but in an equivalent way. So the rest of the problem in terms of thinking, how do we take a number down to a power of 10 is kind of tedious and like working in cases. Like, for example, we can realize that, so let's take the number 843. So we need to take it down to 100. So we definitely see that we have to, how many times do we have to decrease? We definitely have to decrease by the sum of digits minus 1. Like, we definitely need that many times to decrease a digit, right? So this is how many like type 1 operations we need. But then the tedious part is counting how many of type 2. So the things you need to consider are like, is the 1's digit a 0? So if it's, so it's like if the 1's digit, like typically you might think we take the digit in the 1's position, we take that to 0, then we shuffle and get a new non-zero digit in the 1's position. We take that to 0 and so on. But if it starts with a 0, that means we have to do like one more of these arrange the digits operations to like put the first one in that spot. Another thing to think about is, like, is there already a digit 1? So the issue that this creates is that, like say we have a number like 801. Then it's not optimal to decrease this to 0, then swap. Actually, you can't even swap because you can't make a leading 0. But like if there's a 1, you want to keep that for the highest position and then decrease this to 100. So there's all of these cases you have to think about, and it's pretty tricky to get it right the first time, or to like find the one case you missed. And I guess there's a few others like you should think, like say you have a number like 800. You actually can't rearrange the digits without creating a leading zero. So the only option is to decrease by 1. That's the only option. So yeah, the solution is just to consider all of these cases, and it's a little bit hard to know when you're done. but the idea is somewhat straightforward, and like we want to decrease the number of digits, so clearly we have to bring it down to a power of 10. Does anyone else have anything to say?
Cool. So, Richard and Trung, do you have things to share on it?
I found this problem easier actually by thinking about how it would work if you built it up instead of
okay.
put it down.
Did you?
But,
yeah.
I guess
Yeah.
the difference is not that significant. I guess it's always need to, because I guess I thought it a little bit, just realized, well, if it's if there's the things like 800 anyway, you need to. I guess you need to deal with those special cases, whether you're going up or going down.
Yeah, this problem just has so many cases. It's extremely easy to miss a few, and maybe it can be helpful to write like a brute force.
But you can't really do large number for brute force, right?
I mean, I wrote a brute force because I see. The same with like the number of digits, right? Like we know that we eventually have to get to like 10,000 or 100,000 or however many digits there are. So there's always like a set amount of steps, and like the formula is actually like really easy because it's just 9 plus 19 plus 29 plus however much, and then after that you just brute force the rest of the digits through, and it's fine.
I guess okay. I guess the brute force can do it using graph. If you represented the graph and the shortest path, you can brute force up to, I don't know, I guess tens of thousands. That should be enough to.
If you want to, if you're missing, like if you're getting a wrong answer and you have no idea what case you're missing, it can be pretty.
Oh yeah,
it can be a good use of time to just write a brute force and then compare your answers. Then you can generate the tests that you're missing, and then think, how does that fit in with your tests? Like what did your cases not consider?
Yeah.
So
yeah.
So even in like a case like this where the case works really bad, you can still manage it if you're feeling completely lost.
Right. Did you get any time to look at C, by the way? That looked like a pretty like it seemed easy at first, but like the more I looked at it, the more difficult it got.
I didn't spend a lot of time thinking about C actually.
Okay, then that's fine.
Yeah. Are there any other questions you want to discuss? Any problem you want to discuss?
K
What
is
about
the
K?
only other one I solved, I think.
Yeah, we can look at K.
F I have some ideas about too, but maybe I won't discuss. I don't know.
I think that's okay. I think we can be done with K, because I think realistically we're not learning how to solve those. It's not too relevant for preparing for ICPC.
So the problem K is.
I actually haven't looked at this, so.
Well, here's the problem. You're given a permutation, and you want to sort it. The only allowed operation is to take a subsegment that is increasing or decreasing, and reverse it.
This is not the. Was there one about the swapping? You can do swapping with that.
So we definitely know that there's bubble sort, which can always sort an array by swapping adjacent values. And swapping adjacent values is always allowed here because like it's just has to be increasing or decreasing. So 2 adjacent values will be one of the 2, and you're allowed to swap. But the problem is that we're given a limited number of operations, and bubble sort would take at most O of n squared. Well, here we're allowed exactly one. We're allowed at most 191, and n is at most 100.
Was the constraint tight for this problem, or was it another bait?
What do you mean? For like 191?
Yeah.
I don't think it's tight.
Okay.
So the first observation I made was, well, first you can realize 191 is pretty close to 200. So we might think if there's like if there's a solution that uses 2 n swaps. So, or 2 n reversals, that is. So I guess one thing to clarify is that sorting takes n log n, but this is, so the fact that we're doing 2 n operations doesn't mean sorting can be done in linear time. It just means like it just means the time we're doing isn't only the operations, right? Like we're doing more work than just that. Although I guess it's a permutation, so really sort actually is O of n.
So you're given a permutation, and then we are trying, you're allowed to select the range and then reverse everything in this range to get it sorted?
Yes, but we can only do it if it's increasing or decreasing. So like I can't apply it to here because 312 is not increasing and it's not decreasing.
Okay.
But I can say reverse this 321, and then I can reverse the whole thing to get 123.
Good, yeah. Because otherwise it will be trivial. Yeah.
So the next thing to talk about would be, how do we do it in 2n operations? So we've already thought about bubble sort and ruled it out. What are some other sorting algorithms, even if they're like n squared time?
Insertion or selection? I don't know which one.
There's insertion and there's selection. So selection sort. Selection sort says, where's the 1? I'll swap it. I'll swap it with the first position. Where's the 2? I'll swap it with the second position, right? That's what selection sort does. It doesn't seem to match the reversal thing because the 1 could be over here. The first position is over here, and then we have like some crazy increasing, decreasing within here. So it's like there's no way to sort this out in order to bring the 1 here. So it doesn't seem selection sort would work, right? So let's think about insertion sort. What it says is we're going to, like for every prefix, we're going to sort the prefix. And then the next value, we will insert it where it belongs.
Oh my God, big brain.
Right. But we can realize we can actually insert it in 2 operations by reversing this, because this is sorted so far. So let's say the values look like this. So now we reverse it. Wait, I can't imagine this. Okay, it's like this. And then here's the new value we want to insert, right? Now we can reverse this because it's decreasing. And then the new value ends up where it needs to be. Is that clear?
Mm-hmm.
So actually, there is a somewhat simple way to think about how you can do it in 2n operations. But unfortunately, they didn't ask for 2n operations, they asked for 191. And I'm not sure what the intended solution is, but my solution is let's say we're given the permutation. We could, let's say we sort the first k of them however we like, and then we do 2 operations to finish the insertion sort. This would be 2n minus k. Right. So like, let's say f of k is the minimum number of operations required to sort k elements. then the total cost is this. And we want this as less than or equal to 191. And let's say it's for the worst case, so like this would be 100 instead of n. So what I did here was I said, k is probably small. So let's brute force for small k. Find the first one that satisfies this property. And then my algorithm is, I have the brute force, so I know the smallest number of operations to sort the first k of them with my brute force, which is something like k factorial times k squared or k cubed or something like that. That's how much time that part takes. But I find the smallest number of operations it takes. And k satisfies this inequality, so I can do like the normal insertion sort thing to insert the rest of them in. So I was fortunate enough that this f of k like satisfies the property for somewhat small k with like, I think I used 8.
Interesting.
I guess I can believe this is the intended solution, even though I don't know. But
so we don't.
it's
Really
cute enough that I can believe this is intended.
I thought of things that are strictly better than 2n, but I wasn't like I didn't see why anything would like be strictly 191 or less. Like one example would be, we don't have to necessarily maintain the sorted range in the beginning. What we can do is like maintain the sorted range in the middle and then insert things from the sides. But it's still not obvious to me why this would be 191 or less. Because like, let's say we,
I think they said in the what is it called? The problem description, something like there is guaranteed to be a solution. So they probably chose the test cases to fit under 191. Maybe.
I actually think that like there is actually a solution. I was thinking that type bound might be. Is there feedback? I think so. I think the actual bound might be
echoing a little bit. Yeah. Okay.
The type bound might be 2n minus square root of n. That is based on the fact that like either the longest increasing subsequence or the longest decreasing subsequence is at least square root of n. So I was actually thinking about that direction yesterday, but I couldn't figure out the details, so I ended up doing something hacky.
I see.
So
did
you solve this problem using a different method?
Yeah, I did use a different method, but it's
still
based on hope. It's still based on hope.
Yeah. Do you want to explain that?
Sure, I can explain that.
Should I stop sharing?
Sure. Yeah. Trung, do you want to share your screen while you explain?
Sure.
I guess I may need to.
Wait a minute. Yes, I can see it now. Let me just. Okay. Can you see this now?
Yeah.
Okay. So my solution is the same as Riley's.
Just echoing. I don't know whether Riley, did you mute? I don't know.
I should have muted my microphone.
Okay. Try and go ahead. Yeah.
Okay. So let's extend the insertion sort algorithm. So in insertion sort, we go from left to right, and then at each positions, we basically insert this into this into the correct positions before, right?
Mm-hmm.
Okay. So instead of doing from left to right, I do it like this. I start from some middle positions, And then each operation, I chose to extend either to the left or to the right. It means that I chose to insert the left, the value just to the left into the sorted array, or I choose to insert the value from the right just to the sorted array. So there's like two ways to insert into my current subarray. Yes, so either extend to the left or extend to the right. So in the worst case, this is still 2 times n because we need to extend like n times, and then each operation we need like 2 times at least, like at most 2 operations to insert it into our subarray. But however, there are some edge cases where this might not happen. So one edge case is, for example, my subarray is from AL to AR. And let's say this is sorted. Then one of such case is that AL minus 1 is less than all of these values. I mean less than, yeah. Then that way, I can just extend it to the left, and and I also have like a sorted subarray. Similarly, one other case is that AR plus 1 is larger than all of these values. Then I can just extend it to the right, and I also have like a sorted array, a sorted subarray, without using additional like reversing operations. So what I did was I basically used this fact to calculate DPLR, which is the minimal amount of operations to make the subarray L to R sorted. And then I use this DP table to trace back which operations should I, which side should I extend at each step. Does that make sense to you?
Yes, yeah, at high level, yes.
Yeah, that's what I did.
I mean, but in like the worst case of like a fully reversed array, like this method.
Okay, so for a fully reversed array, what I did was basically to first reverse the array and then do it.
Like, yeah, so I was wondering whether there's something you can calculate and then decide to choose one of them, and then just starting from middle extend, and then they'll be guaranteed that you'll be lucky a sufficient number of times. I don't know.
Also about the solution, I can see that if AR plus 1 is less than or greater than everything in there, like then it works.
So there are also some savings.
Like if AR plus 1 is less than everything in the subarray, then you can do 1 operation instead of 2.
Yeah, that's true.
And that should do fine on the everything's reversed case without treating it special.
Okay.
Yeah, that's the solution.
It's still pretty nice though.
I really want to discuss F because like I think it's very educational. Actually, that's my favorite problem of the set. Let's see F. Okay. So basically, the problem states that there are n. How should I say this? There are n values. There are n elements in an array. You need to construct the array such that each element is between Li and I think it was AI and Bi. And then for each, the sum of all of these is equals to T. And then for each element, you can also calculate like the parameter Yi, and you need to minimize the sum of x. X is the array. Sorry. So you need to minimize the sum of x minus y squared divided by y squared. Divided by y, sorry. All right, so this is the problem. So first we can calculate.
So is the yi given or you choose?
Yeah, yi is given. You can calculate yi from the from the statement.
Okay, so you're basically given AI, BI, YI, and then you're trying to construct XI that
Yes. Such that the bounds for each
okay.
is yeah.
Here, and then sum is fixed, and then you want to minimize.
Yes,
or-
we want to minimize
I
this.
see.
And yeah, the problem with this problem, like the issue with this problem is that the answer is a double. It's not like an integer or something, but it's actually a real value. I will address this later and say why that is the case. But first of all, let's try to extend this. We have xi minus yi divided by y. So extending it, we have xi squared divided by 2xi yi plus yi squared divided by yi. So that means we have xi squared divided by yi minus 2xi and plus yi. And we need to minimize the sum of this. We can see that yi is pre-computed, so it's a constant. We can also see that the sum of minus 2xi is just minus 2t. So this can be discarded too. So what we have left is to minimize the sum of xi squared divided by yi. All right. Oh, and it's also worth noting that yi is actually always positive. So yeah, there is no negative shenanigans here. Okay, so let's just for a second ignore the fact that the answer is a real value, and let's try to focus on like integer values for x only. So we need to notice that the function xi squared divided by yi is what is it called? It's a convex function or concave, I don't know. So that means that like the difference if let's say if we increase xy by 1, then the difference it makes keeps going up. Does that sound clear?
Mm-hmm.
Yeah. So because it has this convex function, I believe one of Riley's problems on code forces actually uses this fact. So the solution would be at each moment we choose a value like an index y such that this difference is as small as possible, and we increase in that direction. Yes, and that will guarantee us to have like the smallest sum of this, because after we choose this, after we have increased by this, that means that we added this difference to the answer, and then that difference just keep increasing, and then we can just put it back into the priority queue.
Yeah, just to repeat what's obvious. So basically, you start each xi from the lowest AI, and then their sum is less than t. So you need to add to one of them. You choose it based on this. What you just said.
Yes. Yes. Yeah. Yes. All right. So the problem with that is obviously the answer is not an integer. But what we can do is the step currently, the step is 1, right? What we can do is decrease the step by half, like say 0.5. So it becomes smoother. All right, and when we can repeat that same, we can actually just repeat that same process as before. All right, so let's think about what happens if we decrease this step towards like infinitesimally small. Then when we decrease this step by like infinitely small, then what we're looking at is basically the difference between this function and then the difference between this function and then with this function with epsilon. Sorry, let me just take those graphs out of the way. If the step is like really small, step is like small, then what we're looking at is the difference between this function and this function. And this goes towards the derivative of x squared over I, which is 2x over I, 2xi over yi. And that, because that is the case, then you can think of it as at each moment you choose the index x such that this derivative is as small as possible, and then you increase it by that step. Does this adhere? Does this sound clear?
Yeah.
Yeah. So at the end, what we're looking at is that basically for all of the x's, this derivative must be equals, because like if there are two if there are two x's such that the derivative is not equal, then it is either the case that one of this has reached its limit, or yeah, it is either the case is that one of that has reached its limit, or like the process is wrong because we need to keep increasing them, like choose the one with the smallest derivative and keep increasing them. Does that sound like does that make sense to you?
Yeah, and
yes.
I think this, something like this show up in kind of optimization. Yeah.
Yes.
Yeah.
So my solution is to binary search this derivative, and then find x. Yes, binary search this derivative, and then find x, and then check if the sum of x exceeds t or not.
But I don't understand this binary search. Why binary search?
So that is because after each step, the minimum of all of the derivative just gets bigger. Because imagine that after each step, we take the smallest, like the x with the smallest derivative, and then we increase it by that little step. So the derivative for x just gets bigger, right?
So binary search for what? For xi, or binary search for derivative?
Binary search over the derivative. So that means that we binary search this value.
Oh, I see.
2xi over yi. And then if we binary search this, we can basically calculate all of the x's, and then we check it against the sum of t.
I see. Yes. So your binary search the target derivative. So every value should have that derivative or the max value that's allowed. So.
Yes.
Okay. Cool.
Yeah, that's F.
Okay. So does anyone else have either questions or thoughts to share? No? Okay.
No,
well,
I don't think so.
Thank you, Riley and Trung.
Mm-hmm.